Hi, it's time for another math easy solution. Today we're going to discuss further into conic sections and polar coordinates, and now look at example 4. And in fact, I'll be revisiting example 3 in this example 4 video. So let's just jump right in and look at this example, which states, find the equations of the asymptote lines for the hyperbola from example 3 in both polar and Cartesian coordinates. Yes, so what we have to do is first recap on the example 3 video. First recap on where or how I got the asymptote lines from example 3. So let's just look at the solution. So recall from my earlier example that I sketched the following conic section, which turned out to be a hyperbola, which is right here, r equals to 12 divided by 2 plus 4 sine theta. Then divide both sides by, well, 1 over 2 to get it in a standard conic polar equation formulation. We get this one right here, and you graph it. There it is in red. It's a hyperbola, and this is the directrix y equals 3. And also now note that we determined that the asymptote lines were simply parallel to the polar angles theta equals 7 pi over 6 and theta equals to negative pi over 6, but in fact it could be just positive pi over 6. So if we draw this out like this, and if you have this line, this was the angle 7 pi over 6, the way I derived this one in my earlier video. So 7 pi over 6 is this angle, and in fact that is just going to be parallel. If you look at the center of this hyperbola, it's by symmetry. This is 1, 2, 3, 4, 5, 6. So it's going to be in between that. In fact, that's going to be at this point right here. So if that is at 2, so then 2, 3, 4, and then this can be in between. It's exactly there. This is at 4 and pi over 2 in polar angles. So this is going to be pi over 2 like that, which is just 90 degrees. So that is the polar coordinate of it. And this angle right here is going to be, draw this out like this, bit better. Yeah, so here I just drew that a bit better, fix this line up a bit, and this is going to be parallel to this one right there, so that line. And in fact, we could just go instead over here. This angle is just pi over 6, like that. That's on this way. Then also you could go on the negative side like this. This is negative pi over 6, and this is going to be parallel to the other asymptote line, like this one here. So this is what I just ended up with in my earlier video. So like this is going to be, if I draw one line like that, so parallel to it. Yeah, but now what we want is the exact formulations of these in both Cartesian and polar coordinates. So these are the asymptote lines, like here, asymptote lines. Alright, so let's go ahead and determine these asymptote lines, but first off, also recall that we determined the parallel angles, these ones over here, from the limit of the polar equation itself. So if we scroll up here, here is the polar equation, r equals to 12 over 2 plus 4 sine theta, and I'll now just do a simplified 1 over 2 divided by 1 over 2 like this on top and bottom. Just simplify this. This becomes 6 at the top. 12 divided by 2 is 6. Here's going to be 1. 2 divided by 2 is 1. Plus 4 divided by 2 is 2 sine theta, like this. So there it is. And recall that we know from this right here, r goes to plus or minus infinity. Yeah, just by looking at this formula. So the ray, or the distance from the origin, becomes, or approaches infinity, becomes extremely large as this one right here, as we get a number divided by 0 right here. So as this bottom part, the denominator approaches 0. And this can approach 0 from either the right side, so the plus, or from 0 from the left side. And if it's from the left side, then we're going to get a negative infinity. If it's from the positive side, we get a positive infinity. And this is, let's put that right here, i.e. as, actually instead of as, let's write i.e. approaches 0. Yeah, just fix up the spelling. So approach 0 from the right, but then will be a positive, or left will get a negative, like that. Yeah, because as you're dividing by a really, really small number, that means you can have infinitely amount in there. So this is approaching infinity. So yeah, when we look at the asymptote lines right here, as this is going to infinity, the ray like this r is approaching to this is plus infinity, and then this one right here is approaching, or this r right here, this red, this one here is approaching negative infinity. So r is approaching. Yeah, actually, it depends on which one it is. Yeah, actually, yeah, because of the way that the polar coordinates are set, this could be minus as well. If the angle is all the way here, then you have a negative r. So negative r is going to be opposite of where the angle is, and so on. So again, make sure to watch my earlier videos on polar coordinates. So this could be plus or minus infinity. This also could be plus or minus infinity, and so on. So this approaches plus or minus infinity as this is approaching 0. So thus what we have is thus. So set the bottom equal to 0. So 1 plus 2 sine theta equals to 0. Move this over, then divide it by 2. So what we get is the 1 becomes negative 2. So we'll get a sine theta equals to negative 1 over 2. Like this. So in other words, these are the, or the asymptote lines are parallel to this angle. Our asymptote line. Yeah, so they are parallel to theta in this condition. To theta in this condition. So where the sine of that angle is equal to negative 1 over 2. But in fact, it's also applicable for 1 over 2 as well, and you could see that right here. So if we draw our typical angle graph right here, so recall that sine is, so yeah, let's write this here, recall sine theta, let's erase this for now, equals to opposite over hypotenuse. The opposite over hypotenuse by definitions, opposite over hypotenuse. And if you have something like this, here is our typical angle graph. So this is going to be the opposite. So opposite is, if this is theta, opposite is 1. This is right angle. This is going to be 2, like that. So it's yeah, this is 1 over 2. That angle, and it doesn't matter. Yeah, so if you have it on the negative side, it's going to be on this side right here, like this. Draw this a bit neater. Try to make it identical. So this is going to be negative 1 over 2. So it's this angle all the way over here. So that angle. But nonetheless, you could see that this is all just directly in line with this. So just all parallel to it. So we could just look at this angle, and also then this would work as well, this side like that. So then this is the negative side of it, and this is negative theta, and so on. This is just pi plus, so because we know this is pi. Here's write that inside this. So that's pi. This is going to be, well, pi or 180 degrees plus theta, or tau over 2 plus that, if you have seen my earlier video on why pi is wrong. Anyways, so that is this angle like that, but as you can see, it's all just one line. So we just look at this angle pi. So this is pi plus theta, and this part right here is going to be negative 1, and this is 2 is the distance over there. So, yes, so the only other thing we need to know, as I'll show you why we need to know it, is this part right here. This is going to be, well, this distance is square root 3. And this one here, and recall the Pythagorean theorem. So if that's square root 3, you could see that this is going to be, well, 2 squared, the hypotenuse squared, equals to square root 3 squared plus 1 squared. What we end up getting here is, well, just 3 plus 1 equals to 4, as we should have. Like that. And as you see, this one here, 2 squared is just 4. And that's just using Pythagorean theorem like that. And yeah, so that's what we have. Yeah, so what we have from here is, so thus, instead of saying that they're parallel to this angle, which they are, we could also say, or thus, the asymptote lines, yeah, so the asymptote lines right here, fix that up, have a slope. So the slope's going to be, well, plus or minus 1 over square root 3. So it could be 1 over, yeah, so this is the rise over run. This equals to rise over run, like that. So the rise is 1, the run is square root 3, or you could go with the minus. It's all going to be the exact same angle across like this and that. So that's what we have here. And I'll just write this as equaling to m, like that. So yeah, that's some fascinating stuff there. So now if we graph this out, what we end up getting is, so let's just put this like this. So if we have over here, this is our x coordinate, this is our y. Let's just draw our directrix. This draw the direction a bit lower. This is going to be at, actually make it a bit higher, better this way actually. So this is going to be at our y equals to 3. And again, remember, this is just the directrix based on the unified theorem of conics. And this is the focus right here. We have one there, but also, so the curve looks like this. That's at 3, this one's at 2, like this. It's going to look like this for the hyperbola. And then if we go up 1, this is the 4 and pi over 2. Let's fix that up right a bit further. 4 and pi over 2 coordinate. That's the center of the hyperbola. Then if we go to 5 and 6, this is going to be like that. There's the top part. Yeah, so now if we draw our little lines like that, you can see that's parallel to it. If we just do our rise of a run like this, I'll just go A1, or actually even extend it further. Let's say we have something here, this is going to be rise, and this is, this is the run, square root 3. Actually, better yet, I'll just extend that out. So we have, this is going to be a rise, this is the hypotenuse, this is the square root 3, like that. And if we go downwards here, the only difference is, yeah, it's going downwards here. So this is the rise of, it's going down 1. I'll put everything as positive here, 2, like that. But it's the direction is going down. So you can put a negative if you want, just leave it like that. So that means that this is going to be parallel to this. So I'll draw this now, extend this out, and extend this out like this, and extend this out. Yeah, so when we extend that out, this is going to be, well, parallel to this. So this parallel to this, and this is going to be the exact same rise of 1 over square root 3, and this same thing over here is going to be parallel to this one here, and that slope is going to be a 1 square root 3, like that. So thus in this case right here, what I'll do now is, yeah, so this formula for this in just regular Cartesian is going to be equation of a line, so y equals to plus, I'll write plus mx plus b, so mx plus b. But yeah, since we're doing that, I'm just assuming m is going to be positive. So if we do that, I'm going to then, if it's assuming m is positive, let's write this as here, plus or minus m, like that. So it depends on if we're choosing the positive one for the m or the negative side. So m is just positive there. And then on this side right here, this is just going to be going downward, so we'll just set this as y equals to negative mx plus b. And where the b is just going to be the distance from over here, this is just the y-intercept, so that is just at 4. So thus what we have is, right here, thus, in Cartesian coordinates, Cartesian or rectangular coordinates, right here, coordinates, we're going to have asymptotes are going to be, well, I'll just write that over here. So the asymptote lines are, then it's going to be, well, y equals to plus or minus mx plus b, which this equals to plus or minus 1 over, so rise over run 1 over square root 3, that's our m. Now this is going to be our x, so that's our slope, and then plus, well, b, which is 4, which is the y-intercept over there. So there is our equation like that. Or actually, I'll write this just for more detail, more completeness. So this is going to be a rise over run, and then put that over here. Y equals to plus or minus rise, which is just 1. Run is square root 3, x plus 4, like that. So there is our equation of the asymptote line. Yeah, so now the question is, well, what is this in polar coordinates? So I'll write in polar coordinates, or what about polar coordinates like this? Yes, polar coordinates are polar equations. So first off, recall the relationship between polar and Cartesian. So if you have something like this right here, just move this over. Yeah, like this. So this is going to be our x and y. Fix this up. X, y axis. So let's say we have a line like this. So that's just a random line. And let's say there's a point P on the line. And I'll write P has coordinates r and theta, as well as in Cartesian x and y. Like this. So then from here, if this is the pole, or the origin of the polar coordinate system, and this is also going to be the polar axis is going to be the positive x-axis. Polar axis is this. So this distance from here to here is the ray. That is going to be r, and then there is our angle theta from the polar axis. So in in polar coordinates, this is going to be r and theta. Distance from the pole is r, and that to this point. But in Cartesian, is going to be, well, it's going to be y, the vertical component, and then there's the x component over there. And we can connect these two either with the Pythagorean theorem, or recall just by definition of cosine. Cosine is equal to, well, adjacent over hypotenuse, or just x over r. So then move the r around, it's going to be r cosine theta. Like that. And then y is going to be r sine theta. Because remember, sine theta is just equal to opposite, which is y, over r, the hypotenuse. And then you could just move the r on the other side. And then we'll have for sine. So that's how these are related. And also, remember before I was saying we were looking at the limit as r goes to plus or minus infinity. And that's because, well, the way r works like this is always going to be positive distance, but then if you want a negative r, that just means you're going to have a negative distance. So if this is the angle theta, then what we have is, well, this goes backwards like this, and this is going to be, it's still going to be distance r, but now the coordinate's going to be negative r, and still the same theta. So if you have the same theta, negative just goes backwards along that line. So that's just for reference. So now what we have is, these two right here, and we could just throw that inside here. So we'll write thus. So that's what we have is y equals to plus or minus in Cartesian square root 3x plus 4. And now what we could do is, well, transform this. This becomes r sine theta equals to plus or minus 1 over square root 3x. X is going to be now r cosine theta plus 4, like that. So what I'll do now is, well, I'll shift this over to this side, so minus that, so subtract it, and then also factor out the r. So what we get is an r, and it's factored out. But since we're factoring out the r, we're going to have a sine theta, so we're going to subtract this. But since we're subtracting a plus or minus, so if it's plus, it's going to be minus. If it's minus, it's going to be plus. So what we'll have is a plus. It's going to be a minus plus. So when we subtract it over to this side, what we end up getting, I'll draw this better arrows like that. Yeah, so we'll get when it's minus, the plus is going to be minus, and then a minus of minus is going to be plus, like that. So then we'll have a 1 over square root 3 cosine theta equals to 4, like that. And now what we can do is just move this over to that side. Now we have an equation for r. r equals to 4 divided by sine theta minus plus 1 over square root 3 cosine theta, like that. So this is an absolutely fascinating find right here. So to draw a straight line away from the origin in polar coordinates, is going to be in a form like this. R equals to the b parameter divided by sine minus or plus 1 divided by square root 3 cosine theta, like that. Also, I'll just write that actually right here. So note, general equation of a line. It's a general equation of a line. And I'll write here actually in brackets off center. So it's not going through the center. So off center is going to be, well, r equals to b. That is the y-intercept. So that's b, and then we have sine theta, and then minus plus 1 over, minus plus m cosine theta, like that. So that's the slope. Then we're minus plus, as I'll show. When it's minus, it's going to be the one going up. When it's negative, it's going to be the one going down. Very fascinating stuff. And this is actually a minus plus because m is always positive. But for general, we could just go it's going to be minus, like that. And the slope m is, well, all real numbers, like that. So it's not just always positive in this case, like that. Yeah, so we could just have a negative slope like that. So that is also what we have here. And here, so I just wrote where m is an element of all real numbers. Just recall, it's just a basic conventional way of writing it. m can be all real numbers. So now what I'll do is I'll graph out. So I just want to put this little note there. It came up when I was making this video, actually, just now. Just put that there for reference. So now let's see what happens when we graph the asymptote lines using the Amazing Desmos graphing calculator. So yeah, so let's see how the Amazing Desmos graphing calculator graphs this out, and here's how it looks like. It's a bunch of different ones. It's hard to see where it is, but you can see it's the exact same one. I'll just click it over here. Alright, so it's loading up, and there it is. And what I'll do is I'll just make this in projector mode. And what we have is, yeah, this shape right here. So this is the black, that is just the hyperbola. And then this is the directrix right here. Let's just make that away. And now what we have is, this is just a focus. I'll just remove this. Now here is what we have. I'll just hide these ones here. So these ones are the, yeah, so these are the polar ones. Here is just the basic, yeah, basic Cartesian lines right here for the asymptote lines. So this goes down. I'll shift this over like this. So there it is. This one's going up. That has a positive slope, and then put the -1 goes over there. And now here, when we subtract it, we get in fact the exact same one. Just graphs over top of it. So when it's positive slope, it is a subtraction here. When it's a minus slope, it's an addition here. So it goes over it like that. And as you see, it graphs the exact same line going through right this 4 point there. So very, very fascinating stuff like that. So I just wanted to graph that out. So interesting stuff indeed. So anyways, that's all for today. This is a pretty extensive video illustrating how to draw lines in polar and Cartesian yeah, coordinates, especially in polar, especially when it's off center. When it's at center, it's a pretty basic formula. You could just write, if it's just centered one, let's write that here. So note, it's right here, note, for centered lines, yeah, for centered lines, that's just going to be, well, like this. That's just an angle. Theta, that's it. Theta equals to whatever angle A. That is just a line. So this means that it encompasses all values of R. So R can keep going on and on everywhere like that. That is just for centered lines. And now, yeah, this is draw this better. Make this right in the center, like this, like that. Yeah. So it just goes straight through. So it just always has the exact same angle. I'll draw this one more time, better like that. So yeah, very fascinating stuff. And now the question is, what about vertical lines? What about vertical lines? It's actually a topic for another day. It's very interesting stuff like here. What if you have vertical off-centered lines like this? This one here. This one R equals, what is this? Where the center is here. Very fascinating stuff all together here. Interesting. So I'll just write hashtag stay tuned. I'll definitely be looking further into this particular topic. So yes, lines and polar equations, very fascinating stuff. Here's added this note right here, off center, so not centered, because you could just have a pi over 2 or a 90 degrees go straight up. So the very, very fascinating stuff indeed. Anyways, that is all for today. Hopefully you learned from this pretty extensive example video and on the wonderful world of lines and polar coordinates. Anyways, that's all for today. Like always, you can download these exact notes in a link in the description below, as well as viewing these notes on Steemit. Follow me at MES. I'll upload these notes in article format, and also make sure to check out my Discord chat room and cool math forums, and post any cool math or science related stuff you find. Anyways, that's all for today. Thanks for watching, and stay tuned for another Math Easy solution.